One.
Hello, and welcome to this edition of ALMA Recounts of Cosmic Conundrums series organized by the European ARC Network. My name is Aida Amadi. I'm a postdoctoral researcher at Leiden University and a support scientist at Allegro, the ALMA Regional Center node in the Netherlands, and I will be chairing the session today. The European ARC Network consists of 7 nodes distributed throughout Europe, coordinated by ESO, with their main goal being to maximize ALMA's scientific return for European users. This includes providing virtual or real-life user support to anyone that wants to use or get to know more about ALMA, needs support with data calibration and analysis, proposal preparation, archival research, and much more. But it also includes the organization of talks like today's to celebrate and promote ALMA science in Europe, stimulate and build new connections. In every talk of the ALMA Recounts of Cosmic Conundrums series, a major astronomical question is discussed. The speaker describes the context of the question and then focuses on the ALMA contribution to the field, past and future. The aim of the series is to highlight the unparalleled contribution of ALMA to the broader astronomical landscape and to provide an outlook towards the future. Today, we are delighted to have with us Alvaro Hacar, who will address the question, what is the role of filaments in star formation and how are they shaped? Alvaro completed his PhD on radioastronomical observations of the ISM in Madrid in 2013, after which he took a postdoctoral research position at the University of Vienna until about 2016. He then held a Venni Fellowship position at the Leiden University until 2019, followed by a short stint as a support scientist with us at Allegro for about a year. In 2020, Alvaro joined the Institute for Astrophysics at the University of Vienna as an assistant professor, where he is currently the primary investigator of the ERC starting grant project eMERGE, studying the emergence of high-mass stars in complex fiber systems. Alvaro's research is focused on studying the early stages of star formation in molecular clouds. In particular, he's been using different radioastronomical techniques at submillimeter wavelengths to investigate gas dynamics in these molecular clouds and their connection to the formation of dense cores in stars. Today, Alvaro will tell us about filaments and their role in star formation. So please post your questions for Alvaro in the YouTube chat, which you will find on the right-hand side of your screen. And I will ask Alvaro the questions at the end of his talk. We're looking forward to your talk, Alvaro, so please go ahead. The floor is yours.
Yeah, thank you, Aida, and thank you, everybody, for taking part of this great event. I will start sharing my screen. So I hope you see it now. So as Aida mentioned, so today we are going to talk about filaments and what is the role of these structures and the formation of stars in our own galaxy, but you can understand this question also across cosmic times. I have to admit that, and I thank the organizers for this invitation. I have to admit, however, that the first time I got this invitation, I needed to check, and I Googled what conundrum means, and I found 2 interesting definitions. So conundrum is a confusing or difficult problem or question. Fine, this is what we are trying to address today. But also it's a question asked for amusement, typically one with a pun in its answer, a riddle. So today's conundrum is, as we just said, is the role of filaments in star formation. And this obviously contains a problem. So star formation across cosmic times, how stars of different masses emerge from the ISM. But I will try to also convince you that there is a riddle in this question. And this relates to the meaning of a filament and how we see filaments before and after ALMA, and how we understand the physics of these objects. Before we go into the later results, I would like to also put everybody on the same page and then give you some kind of like overall description of the filament physics and what we knew about these objects. Starting from I mean, something that is really known for almost a century, or actually more than a century ago, which is the role of filaments in the ISM. So the stars, similar to our sun, are formed after the collapse of dense spheres of gas called dense cores of sizes of on the order of 0.1 parsec inside molecular clouds. These cores are typically not in isolation. They form groups of multiple of these structures that they are connected by gas and dust in between. And this is what it forms our filaments in molecular clouds. These filaments have sizes, or we thought had sizes of typically a parsec or a fraction of a parsec, and they dominate the structure of molecular clouds that you see here in the top left. We are still understanding how you create this nested structure of filaments, cores, and stars. Obviously, you have turbulence, you have magnetic fields, and you have gravity, and we are discussing which of them rules this process. But I mean, since its discovery, again, more than 100 years ago, it has been the center of star formation studies. However, this field has been revolutionized in the last about 10 years, when the first Herschel maps of the local ISM were delivered. And here you have an example of the Aquila star forming regions, when you see that basically the entire gas in this cloud, and the dust in this case that traces the gas, is highly filamentary. That basically shift the entire field of star formation and the study of these objects, and we start finding properties of these type of structures. For instance, that these filaments, those that actually seem to be gravitationally unstable, called supercritical, contain most of the low mass stars and cores in these clouds. And one surprising result from Herschel at this the Herschel resolution of between 18 and 36 arc seconds is that in these nearby clouds, filaments seem to have a constant width, which was and still is a matter of strong discussions. With these observations, but also with decades before of models and community effort, a new theory of star formation emerged, explaining the origin of stars in these structures. Here you have like a cartoon where it explains that when you have one of these filaments, you can fragment them and form stars. This is actually a great property of these objects, because the formation of one of these objects becomes natural or comes out naturally of the properties of the filaments. So if you have a filament that is radially stable, and this is done by what is called the isothermal solution for a filament in equilibrium, the Striker filament, you have one of these filaments, and then you apply some infinitesimal perturbation, you fragment them, then you immediately form your cores or few solar masses inside these objects. This is a quiescent scenario where all of this is happening slowly, and then you have a situation that is initially in equilibrium, and then you perturb and form your stars. The key questions here in this scenario is that, if this is true, you need, for this to happen, a filament that is, again, in this equilibrium, and this is described by the mass per unit length of these objects. And for standard filaments in the ISM, this corresponds to a mass of between 15 and 20 solar masses per parsec. The fragmentation properties of these filaments are defined by the radial distribution, is connected to the size of the filament, the width of this filament. And then you can get automatically typical fragmentation scales of 0.1, 0.2 parsecs in length. If you combine these two properties, you automatically get, again, your solar type dense cores to form typical low mass stars. The problem of this picture is that all this is really appealing, and it works nicely for these low mass stars. It also sets an upper limit of which stars you can form in this way. You cannot form more massive stars, basically because your mass per unit length cannot be increased arbitrarily. Otherwise, your filament will collapse radially. The same way you cannot fragment in any other scales, at least not in this picture, this simplified picture, because we know the widths, we know the sizes, apparently, and then this automatically restricts your core sizes and masses that you form after that. Because of that, again, during also the last 20 decades, the last 20 years, different modes of star formation were proposed, and different models for the formation of, in particular, high mass stars, different from this low mass scenario of slowly fragmenting filaments. In this case, the two main models are called the turbulent model, the turbulent core model, and the competitive accretion model, which in both cases you start with a relatively large clump, highly dense, that is either supported by or in both cases are supported by strong turbulent motions until you lose this support, and then you collapse immediately to form a high mass star, or you fragment this massive core initially, and each of the fragments start accreting individually. And in this case, the rich get richer, and you form your high mass stars surrounded by a plethora of small low mass stars. These two scenarios occur much faster than the low mass star formation, and actually again implies and require turbulent motions, highly supersonic to be possible. The interesting thing is that we spent the last 20 years, and actually ALMA was doing this in the past, looking for these precursors, these massive precursors of high mass stars, and the reality is that we couldn't find them. These high mass star clumps that should be before the formation of these objects were never found, because when you resolve them, you see them in more and smaller fragments. So one interesting idea here is that, well, is this hint of that this method or this other model works, and if so, how does it? And actually, before ALMA, there were several questions that were under discussion in the community. One of them, as I mentioned at the beginning, is whether the filaments have actually this universal width. If so, that solves a lot of problems. I mean, brings a lot of questions as well, but it will simplify the analysis at least. The second question is that, as I said, most of the stars are formed in supercritical filaments, so filaments that exceed this critical mass of 15, 20 solar masses. So the question is how these filaments are formed and evolve and even survive, which physically would not be possible, at least in this simplified picture. And last but not least is, so we know, and you have here an example of filaments connected to the origin of high mass stars, but we do not know how then you form these high mass stars in this picture, because as I said, doesn't work in the fragmentation scenario, in the simple fragmentation scenario. So what I want to convince you is that we are now witnessing the ALMA revolution in this field. And I will try to show you in the next slides how these new ALMA observations have changed the way we understand filaments. And actually, they are now shaping a new basically view of these objects, in particular in the formation of high mass star formation. So how we do that? Well, it's thanks to the new ALMA capabilities that came into place. And here I will try to summarize what I think are the most important ones, and I will try to show you some of the key results. And just for you to follow, if you want to see some of the characteristics of these observations, I try to put them always so you can see the details of that. But so the first new capability that ALMA brought into the game is the line sensitivity. So ALMA allows for the first time to observe not only a high resolution, but also detect molecules that are crucial for this for interpretation of these objects. And in particular, for instance, you have a molecule you will see a lot in this talk, the N2H+ molecule, which is a tracer of the dense gas, the gas that is now forming stars. So ALMA allows to map these relatively rare isotopologues, or sorry, rare species in super high detail. And you have here one of the first works on the high mass star forming region by Nicola Peretto in cycle 0, where we were able for the first time in this case, the community was able to observe this molecule. And with this, you can do kinematics. So you resolve these structures for the first time at sub-parsec resolution, thanks to ALMA. And then we start seeing the true origin of high mass stars in the ISM. In particular, these type of structures that you see here, where you have multiple filaments, all of them joining towards a common center. This is called a hub-filament system. And nowadays, we think this is the place where high mass stars are formed. And for the first time, we see them because we can explore these regions at kiloparsec distances with high sensitivity. The second great ALMA capability is the large spectral coverage combined with the sensitivity. So we can map not only one line at a time, but we can do molecular surveys of these type of regions. And this is one of the beautiful examples of the early ALMA science in what is called the brick. This is one of the filamentary clouds in the central molecular zone. And one of these early works by Jill Rathborn, they map, I mean, here you have a sample, but they have many more molecules observed simultaneously with ALMA. And this is the new window, one of the other new windows that ALMA is bringing. And even at the distances of 5 kiloparsec, we can achieve great sensitivity and great resolution together. The third one is that, I mean, we can push resolution to the limits thanks to ALMA. And for the first time, we were able to see now filaments, not in the solar neighborhood, not in the galactic plane, but even we see them now in other galaxies, in this case, in the Black Magellanic Cloud, in a work by Fukui and Tokuda and collaborators. This case, again, much higher resolution, 0.25 arcseconds. But if you have the right molecule, thanks to the combination of these properties, then we see filaments for the first time outside the Milky Way. So with these tools, we are now, as I said, reshaping the way we understand filaments. And to show an example, I have now one of my own, which is perhaps one of the best studied filaments. In this case, we go back to the solar neighborhood, and we are looking at the integral shape filament in Orion. This integral shape filament is one of the most famous filaments where basically everybody has been trying to observe in all wavelengths and all telescopes. And it's an impressive filament because it has a mass per unit length, this property that tells you, in principle, about the stability of this object that heavily exceeds the expectations of this equilibrium solution that we presented before. So we are talking about almost 500 solar masses per parsec. The interesting thing is that this filament is connected to the Orion Nebula cluster. So a region where we are forming 2,000 stars, including several high-mass stars. And this, again, one of the most famous objects, because if we want to understand star formation, in particular filament properties and structure, this is the way to go. We observe this region with ALMA, and it basically changed, at least in my case, the way we understand these objects. Before to show you how it did it, I would like to bring you through the different decades where we observe these objects with this example in particular. So imagine that we are now 20 years back, and then we observe this integral shape filament with a relatively poor single disc telescope. And what you see is something like you have here. So you have a relatively big beam, and then you observe this N2H plus molecule, the dense gas structure of this filament along this region. And you see that, well, you have one filament, at least, with some clumps in between. If you look at the kinematics of these regions, you do this by resolving your lines spectroscopically. You see that this N2H plus breaks, so you have the different hyperfine components. If you don't know about hyperfine, it doesn't matter. Just look at this small component here. You have a really broad component, which tells you that the velocity structure of this particular position, of this clump, should be supersonic. It's a broad line that produces this, or created by the supersonic motions. This was 20 years ago. If you observe the same region now with Herschel, slightly better resolution, things start changing a bit. Your filament becomes more clumpy. So you start resolving out some things. And even some of them have even branches that you already see at this relatively low resolution. So when you move already below the sub-parsec resolution, and more interestingly is that the same position that you thought was supersonic, it starts breaking down in small components. Here you have you see two clearly separated velocity components. We are still an order of magnitude away from what ALMA can do, and you start seeing already changes. When now we move to ALMA, so we now push the resolution to 4 arcseconds, our whole picture changes about how these filaments are structured. So you do not see one filament anymore. You see a really complicated structure with multiple small scale filaments, basically all over the place. You do not see clumps anymore. You do not see these big structures, but just a really complicated fine substructure inside the filaments. Interestingly enough, also, your lines are no longer supersonic. You split your relatively broad lines into much narrower components. And this is also telling you about the physics that is behind these structures. No longer like these big clumps with supersonic motions. There's a really complicated dynamics inside this that we see for the first time thanks to ALMA. Just to show you in a bit more detail, the maps that we got that time, this is already cycle 3. In this case, we combine 12-meter ALMA observation with iron 30-meter, and I will go back to why we do that later on. But so you do this in band 3, and then you see this beautiful substructure inside your apparently one filament that we saw before. This is, again, you can try to analyze the structure, and we did both combining the spatial and spectral distribution or structures. And then what we find is that this apparently single filament is actually a collection, a network of what we call fibers. And fibers is just a name. You can call them like small scale filaments. All of them intertwine, forming kind of like a rope at large scales. That if you observe at low resolution, look like a single massive filaments, but there's actually, a heavily structured gas inside. These fibers, I will not go into details, but these fibers have pretty well-defined properties. So they are quiescent. They have masses per unit length that are close to the equilibrium, this nice value that we want to have to produce fragmentation. And actually, these structures have been seen already before in low mass star forming regions when we are much closer and we have enough resolution to see them. So they are not new in this sense. But the big difference in this case is that these fibers are densely packed in these structures. And you can see here the one scale bar. So in a fraction of a parsec, you can have several of them, and sometimes even dozens of them. Interestingly enough, when you go and look for the high mass stars and the clusters formed in this region, they are formed in these hub systems that we saw before, that ALMA is now revealing for the first time. So what this is telling us is that the origin of stars, and particularly the high mass stars, is connected to these structures that again they are only seen by ALMA at these resolutions, basically because we couldn't see them before. So again, thanks to ALMA, we can zoom in and still have plenty of resolution elements, and then you see these different structures in enormous detail. Again, one of these local hubs where you have this is the famous OMC2 Field 4 object is at the center, and then you have these other low mass stars being formed around them, and then you see how they are at the junctions of these the massive objects at the junction of these different structures. And you can also go to other places in this cloud, and then you see how the other low mass stars basically form along these small scale filaments that we see thanks to ALMA. So our low mass stars still form in the way of fragmentation, but it happens at these tiny little scales that we see now for the first time. Again, only because ALMA now allows us to go to basically the U regime instead of the parsec regime that we've seen before, thanks to, with single dish and with Herschel. Now we go to the few thousand AU resolution, and then you start seeing these effects at really small scales. The interesting thing also is that these filaments are now different, at least look different than the previous Herschel filaments. And you see that now a scale bar here, and then you see like a resolution element. If you make a cut in any of these small scale filaments or fibers, as we call them, you can immediately see that the width of these filaments is no longer 0.1 parsec, is much smaller. We are not the first ones saying this, so there's been already discussed in the past. But with ALMA, you clearly see this effect when you resolve them. When you resolve filaments do not have, at least not in all cases, do not have this apparently universal width, is much smaller. Again, sometimes even close to the resolution of ALMA, which is kind of surprising as well. But again, this is just an example. in the last decade, ALMA has been changing this way of looking at these objects, and we find this type of substructure and subfilaments. It doesn't matter how you call them, but this ultra-rich structure of the gas inside these massive filaments and high mass star forming region. And here you have a few examples. For instance, so Simagiri and collaborators, so this spine that you see here is the filament that you will identify at low resolutions, and they did it with I think Artemis, so a continuum camera. But when you look at the same region in ALMA, and then you use tracers like N2H+ again, you see how this there is no a single axis here, like branches coming in all directions. So the filament splitting and forking in different substructures, telling you that again this is not a unique structure. This is a more complicated gas organization. And the same for other studies like Lee and collaborators. When using is not dependent on the molecule itself, you can have different tracers telling you exactly the same story. When you look at the different parts of this supermassive NGC 6334, you see that again the gas is heavily structured in these complicated networks of small-scale filament that we see here. And again, this is possible only with ALMA these days, thanks to this combination of resolution and sensitivity that is unique. So again, we start seeing this more and more often, and these are a few examples of what people start finding regularly. We see this not only in molecular lines, but we see this also in continuum. So when people start looking at, for instance, infrared dark clouds are or were supposed to be the precursors of these high mass stars in the ISM. So Henshaw and collaborators, for instance, using cycle 2 data, they observe the densest part of one of these infrared dark clouds in continuum. And what you see is that these big clumps, again, the previous idea of how high mass stars form, they do not exist. They break down in small compact objects. And you see this connection in between them, these filaments that connect these different cores and clumps that are, in many cases, much narrower than the 0.1 parsec. And you see here the scale. This structure is really narrow and resolve things to ALMA. We now do this, ALMA does this regularly, not only in small pieces of a cloud, but you can do it in entire infrared dark clouds. And this is a work by Kong and collaborators, also in the continuum. And then you see, again, there is no single axis. This is a really complicated structure that we see for the first time, thanks to this superb resolution that ALMA provides. So as we said, second hint, again, not unique. Filaments are perhaps more complicated than what we think. And last but not least, also ALMA provides or is now producing the first surveys. Again, another property of this telescope that was not before possible because basically we couldn't integrate enough. But now there are different groups doing surveys like the ALMA IRDC, where they sample different objects, but using the same ALMA configuration. That's great to compare the properties. And again, if you concentrate in the compact parts of these objects, you observe with ALMA in continuum, and again, N2H+ is just one of the favorite tracers in this case. Then you see how these structures break down in a plethora of small scale structures. And basically all of them do the same thing. So you have your clumps, you have emission in between the clumps, and this is highly filamentary and then really complicated. So again, what we see is that these massive objects seen at large scales as unique in low resolution, they break down and we see them for the first time thanks to ALMA. So how we put this in context then, and for that I would like to bring you to a recent study that we were doing. So this is part of our review that was submitted recently, where we tried to make sense of all of this information and these ALMA results, but also basically all the filamentary sites that we could gather together to understand, first of all, what is a filament, and second, how we form stars inside them. And this figure that you see here is the results of a meta study that we made. So we put 49 works together, and we put in the order of 22,000 filaments. And we compare two of the basic properties of these filaments. One is the mass in the x-axis, and the other one is the length on the y-axis. And here you have a list of what people have been classifying as filaments. These are filaments in the nearby regions in dark, mainly these Herschel filaments that you saw before, galactic plane surveys, including also Herschel surveys, by the way. You have infrared dark clouds. You have another type of filament that I'm not talking about here, but they are like called giant filaments. So 100 parsec scale structures or filamentary structures. You have also the dense fibers that we saw before, and some other type of filaments. Again, we will not have time to discuss them, but basically, if you look at the molecular filaments, so those filaments that people identify inside molecular clouds and are in this area, they expand over a wide range of scales. What it's telling us is that the word filament is actually pretty ill-defined. And the connection, this simplified question that we had at the beginning, so the connection between filaments and star formation needs to be reformulated. Because after all, and this plot shows it, everything is a filament and filaments are everything. So the question is, what is telling us about the process of bringing the gas from the diffuse phase to the dense phase. And you see here in this plot, and I will go back to see it better. So filaments, what people have been calling filaments, expand almost 8 orders of magnitude in mass and 4 orders of magnitude in scale. So we are seeing structures that go beyond a single definition. We are seeing part of the properties of the ISM itself, which is that it's heavily structured in filaments across all scales. What ALMA is now providing us, again, this is the key part now, is that we are seeing the smallest filaments in the molecular clouds. And sometimes because they are far away, because high mass star forming regions are typically at kiloparsec distances, we only see them now thanks to this telescope. How we interpret them, these structures, is again now the key. And basically how we have this ginormous range of scales becomes the new question. And for that, we need to understand again what we say is a filament and what describes a filament. And basically, again, the problem is that whenever we see something that is elongated, basically 3 times longer than the width, we call this filament. So that becomes scale dependent. But what we can do is to start deriving properties independent of this scale. So for instance, you see here that this is the distribution of all the points that you saw before, these molecular filaments. And you can fit basically the distribution by a mass length relationship on this order. So the length of a filament is proportional to the mass to the power of 0.5. This is a first hint of hierarchy in the ISM, and this has been studied before. It's connected to the what is called the Larson's relationships. But we see now this in filaments because filaments basically sample the ISM structure. We just seen the ISM before was described as spheres or spherical cows, if you want. Now we are seeing them as result structures in the ISM. The interesting thing is that when you look at one of the regions alone, and now I want you to look at the cyan points, which is basically Orion. So depending on the scale that you are looking at, your filament would be placed in one part of this diagram. If you look at Orion as a whole, as much larger than the images that I was showing you, you will put your filament up here. This filamentary cloud at 100 parsec breaks down in parsec scale filaments, and some of them, in particular the integral shape filament, which is this one that you see here, then breaks down into these small scale fibers when we observe them with ALMA. So what we are seeing is no longer one monolithic structure, is no longer one type of filaments. We are seeing a hierarchical structure of the gas in the ISM, described by these filaments. So the question, as we said before, needs to be reformulated. So how we connect the filamentary structure of the ISM on multiple scales to understand the formation of stars. And what is important to remember here is that, again, what ALMA is showing us now is basically one of the key steps in this process. So this hierarchy is set by the properties of the ISM, in particular the turbulent fragmentation of the gas inside these objects. So we start from a really large scale structure, and then it breaks down in multiple steps. And this, you see them in the different masses and different, or smaller masses and shorter lengths. And what ALMA is showing us is the densest part of this structure when gravity starts dominating the process and then start breaking down your filaments to form individual objects. Basically, when things turn more spherical, so to say, and then you start forming your individual objects. This could be for the case of individual low mass stars, as we have seen before, but also is the case of these hubs when you have these multiple filaments joining them. Still, the important thing to understand is that we are seeing this structure, but we need to somehow connect nowadays these other structures that are fundamental to understand the byproduct of the star formation, or basically this cascade of structures. Again, this is only possible nowadays with ALMA and all these new properties and capabilities that is providing. So this is like the general discussion. So what happens now if we look into the future? So what is the next steps that we need to do, at least my personal view on this problem, and how to move forward in these studies. So one main idea is that we are facing a fundamental challenge for ALMA. So as I said, and I hope the message is clear, so ALMA is the only instrument that can do this, that can investigate these objects in enough detail to understand the physics. But this doesn't mean that it's easy to do. And this is because filaments, and as you saw many of the images before, they are typically in really crowded regions. High mass star forming regions, it's obvious that you have a lot of emission around them. And this emission extends over scales much larger than on the synthesized beam, the primary beam, actually many primary beams of ALMA. And because of that, all these observations suffer from an intrinsic property of the interferometer, which is the spatial filtering of the emission. So you see this here, for instance, in this image. So on the left part, you have one of the fields that we observe with ALMA in this Orion region, with the best that you can do with ALMA, at least with the main array. And you see that it's super rich in structure, and then you probably see many of the filaments in there. But these black side lobes are basically these filtering effects. And they have a crucial impact on the analysis of these data. We can discuss this maybe later, but every single property of these filaments is affected by this filtering. And I mean the total flux, therefore the total mass, but also the width and the fragmentation properties. So if we want to recover the true physical structure of clouds and filamentary structure and the connection with star formation, we need to work on this. And the way to do that is to combine these 12-meter array observations with zero spacing data. In this case, we did it with the ALMA 30-meter observations. And then you get these new images that, again, obviously there is strong similarities between the two, but you can see already by eye that the flux and the diffuse structure completely changes when you combine your data. I want to highlight again, and one more time, in a bit more detail, with the work that is done by one of my students, when we are trying to understand this process and quantify it. So in this case, you have, so we were trying different models of filaments with different widths, and then we were comparing the relative error on the flux that we get in there. So negative values means that we are losing flux, and this is on percentages, right? So in this case, we observe the same filament, so a filament of a given width in arcseconds with the different arrays, the ALMA array, the 12-meter array, the 7-meter array, the combination of the two, and the total power. And as you see, and the vertical line describes in one hand the resolution in the dashed line and the maximum recoverable scale, which is used as a criterion to identify this as a problem or not in the observations. As you can see, well, basically all the arrays, all the interferometric arrays by themselves, you start losing flux of these objects way before you reach your maximum recoverable scale. This is a fundamental problem for ALMA that requires attention. And again, it's affecting basically anything that is a bit larger than the beam size, the synthesized beam. You already start losing flux to the point that you can lose basically 50, 70% of the flux quickly. The solution to this is the combination of multiple arrays, but also the zero space in the total power, so you can recover your flux at all scales. This is done now in the new cycles, but this is a warning for the future that this to be done systematically. We are now in the era of large programs, and ALMA is no exception. And of course, it will produce amazing results. And this is in connection with the origin of high mass stars. This is one of them, the ALMA IMF program led by Frederick Mott. And you see, I mean, the results are amazing, but already we are seeing this filtering effect that we should be super careful. But the next step, the future, is going beyond that. And as I said, the connection with the environment, the connection with these other scales is perhaps the next frontier for ALMA. This is going to make observations extremely expensive. Now we are expanding our already large mosaics, high sensitivity observations to much, much larger scales. But this is the key to understand the origin of these filaments. And again, that there is no single structure, that everything is connected to the hierarchy or the hierarchies above them. So even when we have these superb observations and large integrations, we need to start thinking about how to make the connection of these fields with the immediate surrounding. The same way, and this is something that we are, for instance, trying, but many other teams are doing as well, we need to start thinking about how we combine multiple ALMA observations, multiple tracers to understand these connections. No single molecular tracer will tell us the story, no single, not even continuum alone. We need to start making connections between the different gas densities in order to recover these multiple scales and multiple hierarchies in our maps. And this is one example, but again, there are many others. And this is, again, thanks to ALMA, when we can observe these maps, these different transitions in one go. And now we need to make sense of this. We are not using all the ALMA power and all the ALMA data that are produced because we don't have basically the tools to do it. So we need to think about, in the future, how we combine all of these observations. And last but not least, again, we need to go beyond what we have now. So we are kind of limited at this point about which type of filaments we are studying. We are moving, in distance around the solar neighborhood. We started nearby, now we move to kiloparsec scales. We need to go to extreme environments. And here you have a beautiful example of one of these extreme regions, the 30 Dorados region, observed by ALMA. Again, all the capabilities of ALMA now, mosaicing, multiple lines, high sensitivity, multiple arrays. And then you get these amazing maps. And now the key is to understand whether these filaments are similar to the filaments that we observe in the galactic plane, for instance. These are super extreme environments. This 30 Dorados is the largest cluster in the galactic environment. So it's, again, the large magnetic cloud. And there's nothing comparable to this in the Milky Way. So we need to understand, so beyond what we see in these previous plots about local local filaments, how these filaments behave in more extreme environments, and how you form this crazily dense structure like this R136 cluster, which can exceed any of the local clusters that we could imagine. So that's part of the future for ALMA that we need to push also in this direction. Extreme environments, and again, making it expensive, but probably worth doing. So just to finish here, again, this is just an overview. Of course, I couldn't cover all the aspects that connect with the star formation and filaments, but I hope that you now see what ALMA has been showing us. So for the first time, we are seeing this fine detail of filaments that are changing or is changing the way we understand their physics. We see these complex filamentary networks, and you can call them as the way you want, but this is a fundamental property of these structures, and this is the way to understand the origin of massive, the internal structure of massive filaments, cluster as a whole, but in particular the origin of high mass stars. This is a new physics that we need to bring, and that ALMA will contribute. Is the only observatory that can observe and map this type of region with enough sensitivity and resolution. The key idea here, again, and I just draw some lines here and there, and just to give you a hint, but of course there was no time to explain this in detail. But we need to understand that filaments are not unique structures, are hierarchical structures with no characteristic scale. So we see different filaments and different sizes just because our resolution is limited. But we need to understand how we connect these different structures from 100 parsec scale, which is the largest molecular filament that we can find, down to the AU scales that ALMA is now rebuilding. And what is next is basically this connection. This is, at least my personal view, is that this is what ALMA needs to do in terms of filaments. But I can tell you, this is not going to be cheap in terms of observations. Maybe we need coordinated efforts. But the idea is that we extend our maps, our molecular tracers, and we also our tools to try to understand the connection between these scales. So with this, I finish here, Aida, and I will be happy to take your questions.
Thank you so much, Alvaro, for this nice talk, really highlighting the beauty of ALMA with all these images. So since there's a small lag between us and YouTube, I would like to ask people watching to please post your questions for Alvaro in the chat, which you will find on the right-hand side of your screen. And before going to the questions, I will highlight some of the upcoming events organized by the European ARC Network. And actually a link to the agenda of upcoming events will be posted in the chat as well. So there's a proposal preparation community meeting by the German ARCNode tomorrow, which is hosted fully online. And you can watch back some of the previous iTrain talks, the most recent of which was a proposal writing and reviewing talk, which is now on the YouTube channel of the EU ARC Network. And you can find more information on that in the EU ARC newsletter. And the next ALMA recounts of cosmic conundrums will take place on May 4th at 2 p.m. Central European Time, which will be by David Fedele, addressing the question, how and when does planet formation happen in disks? So with that, let me see what questions we have. So there's a question in the chat for you, Alvaro. The question is, do you believe filamentary structures are universal in all star formation environments, such as in high pressure environments in galaxy mergers, or ULERCs, where the ISM is primarily molecular and continuous?
I will say so, because no matter where we look at the in our galaxy, at least in the most extreme environments, and even the Stati Doradus region, we see filaments. And the problem is that we should not think about filaments as these perfect cylinders. It's like the ISM organized itself in these elongated structures. And we are poor observers, poor astronomers who try to make them like cylindrical, but you can think about this as like the result of the non-isotropic physics that happens in these environments. And the physics of the gas cannot change much, no matter whether we are in the local universe or in the ULIRCs, if we will observe with enough resolution, we will see them in one way or another. Maybe different. I mean, the thermal properties might change. If you do not have enough metals, maybe you cool differently, and then you have slightly different properties. But the fact that we see elongated structures is just a result of the anisotropy of the ISM, or the processes acting in the ISM. So yes, I think so.
Yeah, I have a follow-up actually myself. Do you find any trends, for example, towards the galactic center? Like, are there any different characteristics for the filaments?
Well, that's actually a really interesting question that we try to address in this review. The problem is that I will go back to this image, so the plot that we have here. So most of the filaments that you see here are basically galactic plane filaments. So if any trend towards the galactic center, it might be difficult to see directly here. What we see is that when you have these super dense clumps and hubs, and these are marked by these crosses in the diagram, they tend to live in this lower part of the diagram. It's more, so it's explored in the paper, and might take a bit longer to discuss. But basically, what we think is that the normalization of where you find one of these filaments, so they all follow this same mass length correlation and the slope, but the normalization value depends on the accretion rate. In regions in the central molecular zone, you probably have higher pressure, but also higher accretion rates. And then probably will shift your distribution down, and this is how you create these regions here. But one of the key things, and again, we need to push the resolution, we need to push the sensitivity to explore exactly this, the more extreme environments and how they compare with these more like standard galactic plane filaments that we see.
Thanks. Another question. Hi, Alvaro. Thank you for the nice talk. Could you say something about the lifetime of filaments?
Yes, so that's also an interesting question, and it can relate to this plot as well, because the spread of this diagram is relatively small. I mean, for all the filaments, and you can imagine that here are all kind of observational biases introduced by all the studies that we have here. So, and even then, the spread is really small. As I said, the accretion moves things to the right. And the fact that we don't see much of a spread means that you can constrain the accretion rates and then see that the typical lifetime of a filament is on the order of 1 megayear. That means that the filaments that we observe now are on the order of 1 megayear old. But it doesn't mean that you cannot produce more filaments in the area again and again. So that's a different thing. But when we see a filament, it's probably not too old. These things evolve fast, either compress and fragment and form stars, or re-expand again and then disappear. So they are short-living structures in general.
Okay, while you're on this plot, there's a question. Thank you for the nice talk. I don't know much about this topic, but was intrigued by giant filaments and their scale. Could you say a bit more about this?
Yeah, so giant filaments are identified across the galactic plane. And these are, I mean, ginormous structures. These are the largest filaments the largest molecular filaments, I should say, that we identified. So we think that they are probably associated with some galactic processes like spiral arms or spurs, and this is what gives them this relatively ginormous size. Probably they are not unique filaments in a sense that is, again, don't think about this as a cylinder. It's like a collection of clouds aligned due to a potential in a spiral arm, that we try to connect. Again, put observers, and then we see that this is one long thing. This is also telling you about the physics. This plot contains a lot of physics that we do not fully understand yet, but these giant filaments are probably formed again by galactic processes like spiral arms, disfragmentation, while these small filaments, they depend on all the properties like the turbulent cascade and the gravity eventually at some point. So we see these different filaments are everywhere, and and not necessarily the same type of filaments or the same origin of filaments in all cases.
Okay, great, thanks. One more question. Thank you for the very interesting presentation. Do you have any plans to go to even higher resolution now that high frequency long baseline combinations are possible with ALMA?
Yeah, so I mean, but I think also many other groups are doing that. So it's not we are not the only ones thinking about it. But this is an interesting question because, and again, this is one we start thinking about how expensive this could be. So going to much higher resolutions becomes again expensive because you need typically long integrations. But also, if you go to super high resolution, you start needing multiple configurations of even the main array. Because again, one of the other key points I wanted to highlight is that you need to go back to the zero spacing at some point. Even if you observe something that's really small, you still need the zero spacing. So the answer is yes, we are all thinking about it. I think we should forget about individual filaments. We need to start thinking about populations and again, environment, but this is not going to be cheap. I can tell you already. We made the numbers and they explode rapidly, so as you can imagine.
Yeah, I bet. Okay, I have a question for you. You showed mostly the continuum and, of course, the integrated intensity maps, but I'm curious how the kinematics look. Do you find flows sort of ubiquitously across, like from large to small scales? Yeah,
so I mean, there are previous studies on the velocities. So the velocity structure of these filaments, and I mean, some of these works like ours, and again, not only ours, but many others, we identify these structures both in space and velocity. So we see all kind of motions in there. People at even larger scales, and I'm thinking, for instance, about Jonathan Henshaw that does some at larger scales. The Fangstein, for instance, at galaxy scales, you see all kind of motions at basically from the core scale to the galactic scale. The question is how to make sense of this. In some cases, we see order flows. So for instance, this region, I don't have here the image, but you see a converging gradient towards the center of the cluster here, this is the Orion Nebula cluster. And this is probably produced by the gravitational potential of the cluster. And then you see all the motions accelerating and converging to this point. And this is also why you see this like radial distribution. But in many other cases, you see motions, but it's hard to identify the origin of these motions. And this is because probably many of these structures are, again, the result of a turbulent fragmentation, and then there is a lot of randomness in there. So they have their own life, so to say, and sometimes you see something that is converging and it's probably gravity then doing things, but not always. So making sense of this is also one of the important next steps, if we can, because if it's turbulence in the end, there's some chaos in this motion. Yeah, that's what I was trying to get to figure out whether really competitive accretion could be kind of supported by this filament paradigm if there are flows. I mean, it's not competitive accretion, at least in the traditional sense, but you have kind of the spirit in there because so the idea is that when you put enough mass together, and could be mass in these type of filaments and structures, the whole thing becomes gravitationally unstable, like we see here. And then you see the mass flows toward the center. So you accrete to this position. It's not that you accrete into individual stars that they move around and so on and so forth. But you have this region is winning over the other regions that don't have as much mass, right? So in this sense, they are competing for the material. But we think this is the way you grow a cluster as a whole and not just like individual stars locally. Right. Okay, another question. You mentioned that the scale of filaments are driven by turbulence. Can this be described as Kolmogorov scales? Do the densities and length scales in the filaments follow typical log normal distributions or different? So the first part of the question, so whether this is Kolmogorov or not, That's an interesting question that we, I mean, not Kolmogorov directly, but how this connects to the more general scaling relationships of molecular clouds. And what we find out is that this mass length relationship and actually the velocity size relationship that we find for filaments is pretty similar to what Larsson did in the past. What we are now doing is a more modern interpretation of these Larsson relationships in terms of filaments. So the question whether Larsson is Kolmogorov and whether we are seeing is Kolmogorov, we do not know, and actually we are not comparing this. But what is equivalent, or sorry, a way to produce this I will go to the next one, which is this scaling, this particular power scaling, is if this connection between scales is regulated by a turbulent fragmentation. Turbulence in the sense that you break things chaotically. Kolmogorov or not, I mean, the discussion Kolmogorov, Brugger turbulence, who knows? But this type of hierarchical turbulent connection. So the second part is about whether the filaments have PDFs, no? Or can you repeat the second part of the question?
Yeah, if they follow typical log normal distributions or different.
The question is how do you define this in something that is hierarchical? Because I mean, we define PDFs of clouds as a whole, and then they have some kind of power law distribution, right? But then how do you isolate a part of this that is connected to the environment and then connected to multiple scales? I will not know how to do that. There have been studies on how you can combine. So how you produce global PDFs from individual PDFs of filaments. But I think that the problem, and again, the change in mentality that we all need to do is that we need to escape from isolating objects, in this case, filaments, and try to analyze them as, is this doing that? And the next one is doing that. It's like, no, everything is connected to the environments, and how you interact with the environment is the key. So some of them will have more like power law if they are more gravitationally dominated, some others will not. But it's difficult to even isolate them.
Okay, thanks. So I have one final question for you, going more to the technical side of things. So you've really clearly shown that having single dish observations are vital for this field of research, and that not even ACA combined can do that, right? It's really, you need the single dish observations to get the total flux. I was curious how different ways of combining the single dish affects your results. Do you find any systematics there?
Yeah, I mean, this is something that we are exploring these days. I mean, not only us alone in Vienna, but in a much larger group led by Adel Plunquet at NRO. So we are trying to explore all the available tools for data combination and techniques and approaches. And we hope that we can soon give an answer on how to do it and what is the best way to do it. So we want to test these different combination techniques and also be able to assess the quality of these data combinations. So far, I don't want to anticipate results, but so far, I mean, there's like already a big jump between not combining and combining, no matter which method you use. So at least use one that you like, doesn't matter which one. And then that, for instance, if you use feather, which is the standard CASA method, that already puts you in the 10% error compared to 100% flux losses, or, I mean, not disorder, right? So first combine, no matter what, do your combination. And then what we are now trying to explore is among the other methods, including feather, that you have SD-in, you have the TP2Bs, and you have, for instance, a model-assisted cleaning. Which ones bring you to the next, I mean, to the 1% level error? And if so, when this works and when it doesn't. But I don't want to, again, anticipate what is the best one, because actually probably will depend also on the region itself. Bottom line, anyways, again, do a combination, no matter which method, it will improve by far. So
Thanks, Alvaro. Thanks for the tip. Okay, so in the interest of time, I think we should finish there. Thank you all for the questions. And I'd like to thank Alvaro again for his fantastic presentation and all the participants for your attention. If you have any questions about future events or would like to make use of the support offered by the European ARC Network, especially now in preparation for the ALMA Cycle 9 deadline, please do not hesitate to submit a help desk ticket or contact one of the nodes directly. The next ALMA Recounts of Cosmic Conundrum talk will take place on May 4th at 2 p.m. Central European time by David Fedele, addressing the question, how and when does planet formation happen in disks? And we look forward to seeing you then. Goodbye.
Thank you. Bye.